Hello everyone, welcome to this lecture. So, in this lecture we will design a one round PSMT protocol based on Reed-Solomon codes. So, just to recap, in the last lecture we had seen the relationship between Reed-Solomon codes and Samir secret sharing, right. We have discussed extensively that the vector of shares which is computed as an output during an instance of Samir secret sharing can be visualized as a Reed-Solomon code word corresponding to sender's message being the secret to be shared, followed by the random coefficients which are picked as part of the Samir secret sharing scheme. Okay. And we had also discussed the Reed-Solomon error correction property in some previous lecture. So, imagine there is a code word corresponding to a message, Reed-Solomon code word corresponding to some message which is computed and communicated to the receiver, and suppose some of the components get changed, and the goal for the receiver is to recover back the sender's message. For that it is sufficient to recover back the sender's polynomial, even if there are some of the components which got corrupt, where the identity of those corrupt components, incorrect components will not be known. So, that is a decoding problem, and we have seen that from the bounds which are dictated by the coding theory, the decoding is possible as long as the difference between the size of the code word and the message is at least twice the number of corrupt or incorrect components which the decoding algorithm would like to error correct. And we have seen also a decoding algorithm for the Reed-Solomon codes. Okay. Now, based on all these things we will see how to design a one round PSMT protocol. So, just to recap, PSMT stands for perfectly secure message transmission problem, and one round means we have only unidirectional wires from S to R. That means R cannot communicate back. And we had also discussed that the condition n greater than 3t is a necessary condition for any one round PSMT protocol. Okay. We have derived this necessary condition. So, assuming you are given at least 3t plus 1 channels, unidirectional channels from S to R, and at most t of the n channels could be Byzantine corrupt, we want to design a one round PSMT protocol. So, in this protocol all the operations will be done over a finite field, and as a setup we will assume that there are n publicly known non-zero distinct elements. So, publicly known non-zero distinct elements, and all the operations will be performed over a finite field where the size of the field is at least n plus 1, and sender's message also will be an element of the field. So, you might be wondering how that is possible. What if sender has a bit string, binary string, which it wants to securely communicate to receiver? Well, if that is the case, then we can always map that binary string as elements of the field and run this one round PSMT protocol. So, for instance, if sender has a message consisting of log of f number of bits, then that binary string of log of bits can be interpreted as a symbol from the field, and then sender can run this protocol. If the message size is more than log f, well then sender can divide the message into multiple chunks of log of bits. Each string of log of bits can be interpreted as an element of the field, and then each such field can be securely communicated to the receiver by each such field element can be securely communicated to the receiver by running this PSMT protocol. Okay. So, those are some standard mapping issues, okay. Standard mapping things which we do not want to go into details. We assume here that sender has some message which is an element of the field and which is known only to the sender, and we want to design a protocol which allows the sender to do so. Now, what the sender does here is the following. It picks a random t degree polynomial whose constant term is m and remaining other coefficients are randomly chosen from the field. So, basically the polynomial f of m x is a random element from the set of all polynomials of degree t whose constant term is m. And then sender computes n distinct points on this polynomial by evaluating this polynomial at alpha 1 to alpha n. Let the ith point be C I. Now, what sender sends to the receiver? It sends this vector of values C 1 to C n, where the ith component is communicated over the ith channel. Okay. Before going further, what exactly the sender has done here? Sender has basically communicated a vector of Samir shares for the message m, where the degree of sharing is t, such that the ith share is sent only over the ith channel. Okay. So, the vector is not sent completely over the first channel or the second channel, it is splitted across the n channels, and over the ith channel only the ith share is sent. Okay. And from our previous lecture we know that Samir shares also correspond to Reed-Solomon code words. So, I can also interpret this vector of Samir shares as the Reed-Solomon code word corresponding to a message block consisting of t plus 1 elements m a sub 1, a sub 2, a sub t. Now, suppose receiver receives the components C 1 prime, C 2 prime, C I prime, C n prime. Okay. Receiver will be knowing that the distance between the received vector and the actual vector which sender has sent is at most t, because it will be knowing that there could be at most t wires, t channels which are corrupt here and which will deliver incorrect shares, incorrect component of the Reed-Solomon code words. But receiver will not be knowing what exactly is the identity of those t corrupt channels, t corrupt wires. That is why, and it does not know the sender's original code word as well, because sender has sent it over the transmission. During the transmission, some t of the components could get changed, could get corrupt. Receiver's goal is to recover back the sender's message. To do that, receiver applies the Reed-Solomon decoding algorithm on this received vector. So, let me write out here a fact that if channel wire W I is corrupt not corrupt, sorry, then it implies that C I prime is equal to C I. That means, in the received vector at least n minus t components are correct and up to t components could be incorrect. Now, let us see the analysis of this protocol. The protocol is done and it is easy to see that it is a one round protocol. Why it is one round protocol? Because sender computes everything and sends in a single shot to the receiver, that is all. So, it is a one round protocol. Let us see whether receiver will be able to recover back the sender's message or not. So, how is the receiver recovering the sender's message? By applying the Reed-Solomon decoding algorithm on the received vector. Now, from the results in coding theory, in order that the decoding works correctly for the receiver, the following relationship should hold. The size of the Reed-Solomon code word which sender has sent minus the size of the message block of the sender. And what is the message block of the sender? The message block consists of the elements m, a1, a2 up to a sub t. So, it is of size t plus 1. The difference between these two quantities should be greater than equal to 2 times the number of errors which are present in the vector received by receiver. If this relationship holds, then from the results in coding theory we know that Reed-Solomon decoding will correctly output the polynomial f of f x. Okay. So, actually I have written it here incorrectly. So, receiver basically should compute f of m x using the decoding algorithm, and once it recovers f of m x, it should output f of m 0, because that is what actually is a sender's message. But now we want to analyze what is the guarantee that Reed-Solomon decoding algorithm indeed gives back the polynomial f of m x back to the receiver. For that, this relationship has to satisfy. So, now what is the size of the Reed-Solomon code word that sender has computed? Its size is n. And what is the size of the message block of the sender? The size of the message block of the sender is t plus 1, because it consists of t plus 1 elements. The actual input was m, but to send it, it has picked t dummy components and computed the Reed-Solomon code word. And what is the number of errors which could be present in the vector received by the receiver? At most t, because there could be at most t corrupt wires. So, is this relationship true? Answer is yes, because we are working with the condition n greater than 3t. So, since n is greater than 3t, this condition is guaranteed, which ensures that the Reed-Solomon decoding algorithm will recover the polynomial f of m x for the receiver, and hence the receiver will output the correct message. So, the correctness is proved, or the reliability part. So, this proof is for the reliability. So, recall that there are two requirements from the PSMT protocol. The first is the reliability property, namely the requirement is that irrespective of what adversary does over the t corrupt wires, receiver should be able to output the correct message at the end of the protocol, and that is what we have proved here. We now want to prove the privacy, the second requirement from PSMT. And what is the privacy requirement? The privacy requirement is that whatever information adversary sees over T wires, that should not help the adversary to learn about sender's message. Okay. So, how much information adversary learns in this protocol? So, imagine adversary sits over the first T channels, or it could be any T channels. It learns T shares from this vector of length n. Now, what this vector is? This vector is a collection of Shamir shares, okay. And what was the degree of Shamir sharing polynomial? It is a random t degree polynomial, and we have proved in our earlier lecture that in a secret sharing scheme, in the Shamir secret sharing scheme, if there is an adversary who gets at most t shares, its probability distribution is independent of dealer's secret, and that is what precisely is happening. You can imagine the sender as a dealer, and he is sending 1 share over each channel. In the worst case, T shares might get compromised because they might be observed by the adversary. So, adversary corresponds to T corrupt shareholders And in the context of Samir secret sharing, we have proved that even if adversary learns T shares, its probability distribution will be independent of the dealer's secret, and dealer's secret here is nothing but the message for the PSMT, and that shows that adversary fails to learn any information about the message even though it is computationally unbounded. Okay. So, that proves the privacy property, and you can see that this protocol is highly efficient. Right. Why it is highly efficient? Because it requires only simple computations. What are the computations required here? At the sender's end, it requires computing Shamir shares, and at the receiver's end, it requires running an instance of decoding algorithm, and all of these are field operations, finite field operations, and there are very fast algorithms, standard fast algorithms to perform finite field operations, and that is why the computations which are performed here are very efficient. So, that is why this protocol can be deployed in practice without any difficulty. Okay. So, it will not be a computational bottleneck for you, okay. And it gives you a very strong security guarantees in the sense that even if the adversary is computationally unbounded, still it cannot figure out what exactly was sender's message. The only disadvantage that you might say here regarding the protocol is that it requires a lot of channels, lot of wires between S and R. So, for instance, if I take n equal to 100, then this protocol will work as long as up to 33 wires are compromised. So, even if 33 wires get compromised and remaining 67 wires are uncorrupt, this protocol will work, but that requires a very significant proportion of honest wires, uncorrupt wires compared to the corrupt wires. But with that price, you are actually getting very nice guarantees, security guarantees, namely perfect security, and that too with high efficiency. So, the one round protocol that I had discussed in today's lecture was presented in the seminal work by Dolev et al., which introduced the PSMT problem. And if you want to know more about the PRMT and PSMT protocols, you can refer to this thesis. Thank you.